Overmolding is an injection molding process that allows an additional layer of resin to be added to an existing molded part to provide a combination of characteristics that no single material can provide. One of the most common applications is to add a soft, functional, hand-friendly layer of rubber-like material, typically a TPE over a hard substrate. Another is to change or enhance the appearance or cosmetics of a part by overmolding material of a different color or finish to it. Overmolded materials can be found on anything from medical devices and hand tools to toothbrushes and as gaskets and seals within assemblies. There are two primary methods for overmolding: two-shot molding and pick and place. Two-shot molding requires a single production mold while the pick and place requires two molds. Material selection for overmolding can be complicated. Substrate and overmold resins can complement one another, but to be effective, they must be compatible. Choices vary not just with the application of the overmolded part, but also with the method being used to produce it. Because process and outcomes are more complex for overmolding than for single-shot injection molding, it is helpful to seek input from resin experts when selecting materials. See the following chart for compatible resin. This chart shows the compatibility of resin for overmolding. Two-shot molding involves a substrate that is molded in one material and then quickly overmolded with another material. This is generally a highly automated process. The second method is pick and place molding, in which an entire batch of substrate parts is molded. The substrate parts are then manually placed, one at a time, into a second mold into which the overmolded resin is injected to produce the completed parts. There are three primary methods for two-shot molding. Transfer overmolding is a robotic procedure in which substrate parts are mechanically lifted out of one mold and placed into another, larger mold. The overmolded material is injected to fill the empty space in the second mold, typically while the next substrate is being produced in the first mold. Rotational overmolding is another robotic process in which the mold itself moves from one injection station to another to allow injection of substrate and overmolded materials. Core-back overmolding can be used only with very specific linear geometries. The mold is built with a sliding section that is pulled back after the first material is injected and set to make room for the second injected material. All three two-shot methods layer the overmolded material onto a warm substrate, which aids chemical bonding. All three also require specialized equipment and expensive molds, but because they are highly automated, they are cost-effective for high-volume production. Pick and place molding uses two completely separate molds. A batch of substrate parts are manufactured in one mold and allowed to cool. They are then placed, by hand, into the second larger mold, which accommodates the substrate parts and leaves room for the overmolded material to be injected over the substrate. The process uses less complex equipment and simpler molds than the two-shot methods and simplifies and accelerates setup. Comparing overmolding methods. While the manual placement of substrates into secondary molds is slower than the robotic processes, it can typically complete production of low to medium volumes of parts more quickly and at significantly lower cost. The biggest challenge in pick and place molding is the reduction in chemical bonding between overmolded materials and cool substrates. To maximize adhesion, substrates must be carefully handled to prevent contamination of surfaces that could impact adhesion. In addition, proper material selection also helps ensure good bonding in a pick and place application. The role of bonding. Bonding between resin layers helps keep the layers from separating. Depending on the part geometry, bonds can be subjected to several forces that can pull the layers apart. These include direct tensile pull causing separation at a butt joint, shearing caused by a pull parallel to the bonded interface causing separation at a lap joint, peeling that typically begins at an edge and propagates along the interface between materials. Bond strength is particularly important when one of the materials is TPE, which can flex and be pulled away from the substrate. This applies to both thermoplastic elastomers, which soften when reheated, and thermoset materials, which do not soften. There are two primary ways in which layers bond. One is actual chemical bonding at the interface of the two resin layers. The other is mechanical bonding, which depends on the physical geometry at the interface. Acceptable bonding is achieved through a combination of part design, material selection, mold design, and molding process. Chemical bonding takes place at the molecular level and is affected by several factors. The first is the wetting ability of the substrate by the injected overmolded material. Better wetting allows more contact between the two materials and more opportunity for bonding. This is a factor of temperatures of the materials, viscosity of the overmolded material, and texture, and porosity of the substrate surface. At the interface, adhesion can take place in three different ways. Mechanical entanglement of the polymer molecules. Co-crystallization. Chemical reaction between the polymer chains. Adhesion can also entail a combination of the three, and a textured surface increases the area over which adhesion can take place. In addition to the need for compatibility of the resins themselves, the presence of additives, fillers, and certain surface treatments can reduce the chemical interactions of substrate and overmolded materials. The material manufacturer can be a valuable resource in identifying resins that both meet the designer's performance requirements of the completed part, and resins that are compatible with one another and able to provide maximum adhesion. Processing can also significantly impact adhesion. This is particularly true in pick-and-place molding. In this process, the substrate is allowed to cool before overmolding and is both exposed to the environment and handled during the process. It is critical that the manufacturer prevent the accumulation of impurities on the substrate surface during storage and handling in order to maximize adhesion. Mechanical bonding can be used in place of or in conjunction with chemical bonding. When overmolded resin flows into holes in the substrate, particularly if the holes are dovetailed to widen at the bottom, the cooled overmolded material is locked to the substrate. Other ways to enhance mechanical bonding include wrapping the overmolded material around the substrate or increasing surface area of the interface with grooves, pickets, posts, or bosses. A porous substrate provides tiny holes into which a TPE can migrate to create a mechanical bond. To prevent peeling, avoid exposed edges of the overmolded material. A raised edge of substrate material can protect the edges of the overmolded TPE where peeling could otherwise begin. These are examples of mechanical interlocks. Factors that affect adhesion. Grade of plastic substrate: glass-filled, mineral-filled, heat-stabilized, lubricated. The more polymer on the substrate surface, the better the adhesion. Ensure that the chosen thermoplastic rubbers or TPE is designed to bond to the substrate. Appropriate thermoplastic rubbers thickness too thin can lead to delamination. Use of mechanical interlocks in the component design. Proper shut-off design. Adequate venting is critical, especially at ends of flow. Type of color concentrate carrier used in both the plastic and the TPE. Pre-drying of the TPE over mold material, if required. Substrate preparation and cleanliness. Higher TPE melt temperature generally provides higher bond strength. Control melt temperature by injection speed, first stage pressure, then barrel temps. To fine-tune, I emphasize the followings. 1. Bonding. A strong bond between the two materials is critical to overmolding. 2. Materials. Substrate and overmold materials should be physically, chemically, and thermally compatible. 3. Principles. The principles of moldability apply equally to overmolding, with a few additional considerations to keep in mind. Following the rules or principles, overmolding reads from the same engineering book as traditional injection molding. Processes, with a few additional idiosyncrasies. 1. Proper draft angles, uniform wall thickness, and smooth transition lines must be maintained in both parts. 2. The thickness of the overmold material should be less than or equal to that of the substrate below it. 3. The melting temperature of the overmolding material should be less than that of the substrate. For if chemical bonding isn't practical, don't despair. Mechanical interlocks are a great way to hold it all together, and should be used wherever possible. For texturing of the substrate workpiece may help with adhesion. Texturing of the overmolded part may provide a better grip and more attractive surface. 5. The surface of the overmolded part should be even with or slightly below any adjacent substrate surfaces. 6. Keep it clean, serve it up hot, watch out for additives, mold releases, demold gently, consistency counts, mechanical interlock. Do a preliminary test. 7. The wall thickness of the substrate and overmold should be as uniform as possible to obtain the best cycle time. Wall thickness in the range from 1 mm to 3 mm will ensure good bonding in most overmolding applications. Design considerations. Shrinkage and warpage. Most TPE compounds have fairly high mold shrinkage in the flow direction with minimal shrinkage in the cross-flow direction. This can lead to the overmolding compound contracting more than the substrate after the part is ejected from the tool. This, in turn, can result in a warping or cupping of the substrate part, usually in the direction of flow of the overmolding material. This is especially true for long, thin parts or parts where the substrate is thinner than the overmold or if a low modulus substrate material is used. This can be partially counteracted by using higher modulus substrate materials and providing stiffening ribs in the substrate. Thinner coatings and the selection of a lower hardness overmold grade will also help. Relocating the gate to influence the TPE flow pattern may also be of assistance. TPE materials are quantified based on shore hardness, which is a material's resistance to indenture on a 6.3 mm minimum thickness molded plaque, ASTM D2240. A lower hardness product has a softer feel on the surface for the same thickness product. But since overmolding is usually limited to thin skin of TPE, the softer feel is influenced by the hard substrate underneath. If a hardness test is done in this case, a lower indenture will be observed, resulting in higher hardness even though the skin may be soft. If the TPE overmold is to be present on both A and B sides of the parts, 2 material molds that shuttled or rotated between mold sections must be used. 2 material molds using moving cores should be used to form a uniform coating on a portion or the complete side of a simple part. Depending on the wall thickness of the TPE and the substrate, the production rate can be very high. Use a higher modulus substrate material. Add stiffening ribs to the substrate part. Minimize the thickness of the soft TPE. Use a lower hardness for the TPE. Relocate the gate to minimize the flow length to thickness ratio. Match compatibility of TPE and substrate. Shut-off design. Shut-offs should be designed to 1. Reduce the potential of peeling and provide a sharp transition between the TPE and the substrate. 2. Provide a distinct cavity for the TPE that is capable of being vented. 3. Prevent the TPE from flashing over areas on the substrate. 4. Provide a 0.003 to 0.005 of an inch interference when using plastic inserts or substrates. To take into account shrinkage, sinks and tolerances. 5. Provide a spring-loaded area if the inserted substrate is a metal or other non-compressible material. An accent groove of 0.015 to 0.03 of an inch depth and 0.03 to 0.04 of an inch width helps to develop a good shut-off. 6. Due to the tolerance on metal and other non-compressible inserts, it is necessary to include Belleville disc springs or high-tension springs in the design to prevent flashing of minimal thickness inserts or crushing of oversized inserts. 7. Resulting TPE geometry must be designed to vent the cavity properly. Shut-off recommendations. 1. Provide interference fit of 0.002 to 0.004 of an inch, somewhat dependent on cosmetic needs. 2. Specific plastic substrate ductility. 3. Heat treat shut-off steel to a minimum 54 Rockwell hardness. 4. Consider substrate edge design to hide TPE edge from consumer. 5. Pre-dry hygroscopic substrate and TPE pellets to avoid porous surfaces nearest substrate interface. 6. Where appropriate, have the actual shut-offs employed as inserts, helps downstream injection mold maintenance. Shut-offs to avoid. 1. Avoid using rounded or radiused shut-offs. 2. Component designs where TPE geometry lies high above the substrate, example cliff wall. 3. Placing shut-offs directly in the mold base. 4. Building the tool without developing a clear shut-off strategy first. 5. Placing the vent directly at shut-off edges can actually encourage flashing. During the design for overmolding phase, identified the risk of collapse to the substrate. The issue arises when the substrate is being filled. As shown in this picture, the gray substrate sits in the mold while the blue TPE is overmolded under high pressure and high temperature. Due to the geometry of the substrate's outer diameter, the original mold design would have caused the substrate to be unsupported during the overmold process. This lack of support on such a tall feature would allow the high pressure of the injecting TPE to deflect the substrate outward. In the extreme, this deflection could cause damage to the substrate. An even more likely scenario would be a flexing of the core pin relative to the part, which would result in an inconsistent wall thickness. Also, movement of the substrate would present gaps in the part and create overmold flash directly into the business area, rendering the part non-functional. I have adjusted the mold design to add slides along the entire outer surface of the substrate. As shown in this image, the red outer support of the long tower helped maintain the position of the substrate along the length of the inner diameter. They then introduced interlocking features for the core stripper sleeve insert to further fix the location from either end of the well. In the image of the modified mold design, the green core above and below the gray part can be seen interlocking into the part itself to create a tight seal. If and when the TPE starts to flash, it would flash away from the business area of the mating component, eliminating the impact to the product's functionality. With the mold design finalized, the mold was constructed, and parts were run with a consistent wall thickness free of flash or deformation. The design for overmolding project phase required more time earlier in the project but resulted in greater time savings for the project during sampling because fewer iterations were required to achieve the desired part. Any damage to a part during the molding process also increases the risk of damage to the mold itself. This risk increases during overmolding and insert molding, so it must be considered with deep care during part design and mold design. Design for manufacturability puts the principle of quality by design into action. Diligent forethought, deep experience, and open dialogue with clients and suppliers provide the ingredients for successful quality by design. Tooling info for your reference: the second shot, substrate must have steel backup walls. For the second shot, use mold flow analysis to verify the hole size for the material pass through. Tooling info for your reference: second shot mold surface. In general, an EDM finish will produce a good surface and good release from the mold, and shall be coated with a Teflon impregnated nickel, after it has been given an EDM finish. When feasible, second shot shall have 1 mm offset below the substrate. Tooling info for your reference: thin blades and details, which may be subject to frequent maintenance or replacement, shall be inserted within the cavity, must use hardened H13 RC 45-52. When feasible, utilize group inserts and cavity core thin steel interlock design, for holding thin blades into position and to eliminate a tuning fork conditions. The intersection of ribs and walls must have a radius of 25% of the nominal wall. The tool maker must check the product 3D data if sharp corners exist, and engineering change to the product data is required, to remove all sharp corners and stress concentrations. TPE venting dimensions: the criteria as shown in this diagram. And if feasible, use self-cleaning ejector pins or through holes for venting deep wells and enclosed shapes. Slides lifters are required when feasible for this specific part design and substrate. Backup steel walls all around are required. The slides lifters to be connected to the ejector plate and not driven by a horn pin. A horn pin slide design is not required for this specific part design for second shot only. Mold temperature for TPE: To prevent mold from sweating and the resultant water contamination in the cavity, the mold temperatures should be set above the dew point temperature in the molding area. Mold temperatures may have to be raised if there are long or thin sections of the part, which cannot be filled by changing other molding parameters. Mold temperatures of 70 to 120 degrees Fahrenheit are typical. When using lifter bar ejection systems, differential thermal expansion of the mold may cause the lifter to jam. Therefore, accurate mold temperature is critical when running molds with core lifters. TPE compounds release from cool surfaces better than hot. It is common practice to use two mold temperature controllers while running TPE. If sticking in the A half of the tool is a problem, reduce its temperature to see if it will help. Substrate temperature. Better bonding can be achieved if the substrate temperature is elevated. For insert molding, preheating the insert may improve the bond strength. Preheating can also reduce any surface moisture present on the substrate and thereby improve adhesion. For two-shot molding, the time between the first and second shots should be kept as short as possible to achieve the best bond. However, it must be long enough for the substrate to develop sufficient properties to resist the injections, pressures and not be remelted or distorted by the second shot. The total overall cycle time is dictated by the thickest wall sections and material plus the time to rotate the mold and to load any inserts. Purging. If the press is down for more than 10 minutes, purge it before restarting production. To prevent flashing, restart the machine using a reduced shot size and gradually increase it to the previous setting. Regrind is not an option for many two-material applications. Up to 20%, regrind may be used if there is clean, undergraded TPE scrap generated during the process. Higher levels of regrind are tolerated in black materials. Natural products, light-colored or clear compounds may show contamination or discoloration unless properly controlled. Organic pigments used to produce yellow, red, blue, and green colors are more likely to burn out or lighten after prolonged residence time or high regrind utilization. When possible, use consistent regrind levels. Support substrate during second shot. Injection molding occurs with pressure against the mold cavity walls. During initial part molding, this pressure fills the cavity to mold the perfect part. During overmolding, this pressure can cause molding issues if the substrate is not supported adequately to hold up under pressure. Proper mold design should include support areas on the substrate to help the second molding process. These support features must have built-in clearance to accommodate for part tolerance deviations. Any ribbing should be kept to a minimum in these areas when possible. The position of substrate part in the mold should be carefully planned for. The substrate part should not move while the mold is closing and during injection. Make sure the material flow is not blocked by the part features. Through holes in the substrate may be required for easy fill. Both sides of the substrate, holes in the TPE may be required for hold pins. The design responsible should plan for these design previsions as they are must-have for the molding process and it can affect the molded part style and durability. Depending on the accuracy of the insert, use a spring-loaded core pin on one side of the metal insert. The spring-loaded pin compress as the mold closes and allow for any small variations in the metal insert. In the example above, the green cavity insert allows a small amount of float, up and down in the image. Some designs may not allow this if the injection pressure would push the pin back. Notice that the core pins, purple and green, interlock with one another. The interlock prevents deflection of the thin pin or the mold thin steel condition. The taper of the purple pin is to allow a slight misalignment for operators or robotics when loading the inserts. When using robotics, you should use docking pins for end-of-arm tooling to make sure the inserts are accurately located onto the pins in the mold. The followings will help you troubleshoot the second shot injection molding process. Thank you for your time. My name is Amer Janineh and please watch my other mold design videos.